Hello students, today I will tell you about the Devison Germer experiment, the demonstration of matter waves. As you all know that De Broglie gave the concept, the hypothesis of the matter waves, that every moving matter particle is associated with a wave, and the wavelength of this wave is inversely proportional to the momentum of the particle. So now, for the first time, this matter wave was demonstrated practically by Devison and Germer. As you know that the main property of the waves is the diffraction. It means that if wave is associated with the moving particle, then it must be diffracted. So this experiment is based on the diffraction of the matter waves. If the particle is diffracted, it means that wave is associated with this. So we have two things: one, the wavelength from the experiment, and second, the wavelength from De Broglie formula. And if the wavelength of these two coincide with each other, it means that this is the highly support of the matter waves. So now let us take the Devison Germer experiment, the demonstration of matter waves. Devison Germer experiment. Demonstration of matter waves. Devison Germer are the two scientists. They both collaboratively conducted the experiment. So if a wave is associated with moving matter particle, it must be diffracted. Since diffraction is the main property of wave. So this experiment consists of three parts. The experiment arrangement as three parts. Number one, electron gun. Number 2, nickel crystal. And number 3, ionization chamber. Here the electron gun, as the name suggests, gun. Gun means that something that accelerates the particle. In gun, what we do, that bullet is there and that is accelerated by the trigger. And in this experiment, what is the meaning of gun? That the electron beam will be accelerated by applying the potential difference. And the electrons are emitted thermionically from some filament, and then they pass through a very fine hole and potential difference is applied across the beam, so electrons are accelerated. So this is called the electron gun. This arrangement is called the electron gun. Second is nickel crystal. The electrons are moving, it means the wave is associated with them, then this must be diffracted by something. So here we apply the nickel crystal. In nickel crystal, the nickel particles are regularly and periodically arranged, and the spacing between the particles or in the nickel crystal, that is of order of the wavelength of the matter wave associated with the electron. Because diffraction, it is necessary. The diffraction will take place only when the size of the obstacle is less or equal to the wavelength of the wave. So looking to this matter, the nickel crystal is selected. So the nickel crystal acts like a diffraction grating. And now the question is that when this electron beam will be diffracted, then how to find the intensity of this one? The diffracted electron beam then goes to the ionization chamber, which is filled with some gas. The electron beam in the ionization chamber ionizes the gas and ions are produced, and this ionization chamber is connected with the electrometer that measures the current. So highest the current, highest is the intensity of the diffracted beam. So now let us see the experimental arrangement of this one. Here is some filament. It has some heating property here. It is heated by some, and this we apply the slits. Here we apply the potential difference. Slit S1 and S2. Here we apply the potential difference. Then the electron beam passes through this fine hole. This is the diffracted electron beam, incident electron beam. This is the nickel crystal. Here we have a circular scale. This is electron beam. This is the angle of diffraction. So this is diffracted beam. This is ionization chamber. This is the circular scale. It is circular scale. Circular scale. This ionized chamber is mounted on this horizontal circular scale so that it can be rotated at any angle. Now here the nickel crystal is just like this. It is nickel crystal. Here the electron beam. This distance is d, and this is the path difference. So much. This is the angle of diffraction. So this we take, suppose A, B, and this is now N. This is now right angle triangle. So this is the arrangement. This is the filament F, which is heated by passing the current through it. These are the two slits which have fine holes in the same direction, and the potential difference is applied between this slit S1 and S2, and then electron beam is accelerated, and then it passes through this slit S here, and then goes directly to the nickel crystal. There it is diffracted by these atoms of the nickel crystal. Diffracted beam goes to ionization chamber. VAT ionize the chamber, ionize the gas, and because of ionization the current is produced, that is measured by this galvanometer. This is galvanometer. Galvanometer. So this is the practical arrangement of this Devison Germer experiment. So now I take all three parts one by one. First is electron gun. The electrons are emitted by heating the filament they are accelerated accelerated by applying potential difference between slits S1 and S2 the beam the accelerated electron beam passes through slit S and strikes the nickel crystal. So this is the electron gun. The main thing is that the electrons should be emitted and they must be accelerated. This is what the meaning of gun. Nickel crystal. It behaves like diffraction grading the nickel particle are regularly and systematically arranged in the crystal. These nickel particles act as diffraction centers the atomic spacing is of order of wave associated with accelerated electron beam. This is what the condition for the diffraction. So here we have the diffract by Bragg's law. By Bragg's law, d sin theta equal to L lambda. So what I told you in the figure of the nickel crystal, the two waves which are diffracted at some angle theta, then they have a path difference, and that path difference is d sin theta, where d is the atomic spacing in the nickel crystal. where D equal to atomic spacing, that is 2.15 angstrom, theta angle of diffraction, and order of diffraction, and lambda wavelength. Order of diffraction means that the electron beam is diffracted by the first layer, second layer, third layer, fourth layer. If diffracted from first layer, then n equal to 1. Diffracted by second layer of the nickel crystal, then n equal to 2. By third layer, then n. So as the beam is accelerated by higher potential, so it will be get higher energy. Then it will be diffracted by the inner layers of the nickel crystal, of the nickel particle in the crystal. And now third is the ionization chamber. Ionization chamber. The diffracted beam of electron goes in ionization chamber filled with some gas. Which get ionized by the beam. The electric current is produced in chamber that is measured by electrometer. Measured by electrometer. It gives the intensity of diffracted beam. The chamber is mounted on a horizontal graduated circular scale. the chamber can be rotated on the scale. So this is like this circular scale, and the chamber is placed here. Then this can be rotated like this, so that the angle of diffraction could be variated. Now the chamber will continue. The diffraction angle can change by moving the ionization chamber. So at different angles we find the intensity of diffraction. Now the method. Or the procedure. The filament is heated by passing current through it. It emits electrons which are accelerated by applying potential difference across the slits. The accelerated beam goes towards nickel crystal. Where it is diffracted. The diffracted beam reaches ionization chamber, where in which the gas is ionized. By beam. The current produced due to ionization is measured by electrometer. It gives intensity of diffraction. The ionization chamber can be moved on circular scale to change angle of diffraction. The electron beam is accelerated by different potential difference. A polar graph is plotted between intensity of diffracted electron beam and angle of diffraction. It is found that electron accelerated by 54 volts have high intensity of diffraction at an angle 54 degree. At an angle 50 degree. So these graphs are like this. Here we take the intensity here, and here we take the voltage supposition of 44 volt, and then we find that the graph is like this angle, and then we find, suppose this is I, this is your 54 volt, and then the is like this, and then we find the intensity, and this is at suppose 64 volt. Then the graph exists like this. So it is found that this angle is 50 degree. This is somewhat less than this. This is somewhat less than this, and the intensity is maximum for this. You can see the graph. The peak of this graph is higher than all these curves. It means that the intensity of diffraction is maximum at an angle of 50 degree when the electron beam is accelerated by 54 volt. So now we find the wavelength. So Bragg's law. D sin theta equal to L lambda for first order diffraction. First order diffraction n equal to 1. So now we are left with d sin theta equal to lambda. Therefore, lambda d equal to 2.15 angstrom. This is now sin 50 degree. So if we put the value, then it is found that 1.65 angstrom. This is now lambda. It is the experimental value. Value of lambda. De Broglie wavelength lambda equal to 12.27 upon square root of V angstrom. So now this is 12.27 upon square root of 54. This is so much angstrom. It is comes out to 1.67 angstrom. This is equal to lambda. This is the theoretical value. It is theoretical value of lambda. Now you can see that the experimental value of lambda 1.65 angstrom and the theoretical value 1.67 are approximately equal. It means that this gives you a big support that the wave is associated with the moving matter particles. The values of lambda found experimentally and theoretically. Theoretically match with each other. It proves that wave is associated with moving electron beam. So this is the demonstration of matter waves. So this is clearly proves that a wave is always associated with the moving matter particle. Though this this is not a very wide difference, so small, and it can be considered to be true. Devison and Germer were successful to show the demonstration of matter waves. You like, share and subscribe this video. Thank you.